Welcome, everyone. Are we ready to get started?
Yes, please do.
Welcome, everyone that's on the webinar. This is the scientific evidence on climate change and its effects on health. I'm Steve McKee. I serve as the Executive Director of Texas Physicians for Social Responsibility. And we are excited to partner with Doctors for Change to bring you this webinar presented by Dr. Robert Haley. By way of introduction, Dr. Haley is a leading expert on climate change and the distinguished teaching professor of internal medicine at UT Southwestern Medical School. He is also, prior to joining the faculty, he was with the Centers for Disease Control and Prevention for 10 years at the CDC. And then in January of this year, Dr. Haley was recognized for a Lifetime Achievement Award by the Texas Medical Association. We're honored to have Dr. Haley with us today, and he's going to be presenting on, again, climate change and its effects on health, with a lot of scientific evidence and research that he has collected over the years. So Dr. Haley, we're happy to have you here, and I think we're ready for you to take it away.
Okay, good. Can you see my screen okay, my slides?
Can see it.
Okay, good. Well, listen, I'm really happy to be here and talk to you today. And I want to talk about the title I've given it is The Scientific Evidence on Climate Change and the Ethics of Skepticism versus Denialism. So we'll have a short postscript on the ethics later. That way, if you want to, you can claim credit for this. Okay. All right. So what I want to do is focus on the scientific evidence and try to divorce yourself from the politics, either one way or the other. And let's focus just on the evidence, because I think when you see the evidence, you see a compelling picture that I think is kind of missing in most of what I see and read. Okay, so let's see. Uh-oh. Oh, there we go. Sorry, I've got my slides at the end instead of the beginning. Okay, here we go. All right, so I have nothing to disclose, no conflicts of interest, no off-label drugs. I only want to disclose a reminder that, remember, this was when Australia burned in January of this year, and there's a visual. I think that's relevant. Okay, I got into this back in 2003 when we did a post-epidemic investigation of the West Nile encephalitis epidemic that hit the whole country, but the epicenter of this for the country was in Dallas and the surrounding 4 counties. And what we found, we had the mother of all epidemics for about since the infection was introduced into the Dallas area in 2002. We had one small epidemic in 1967, which we thought was a big deal. But then it was pretty low, and it almost appeared to go away in 2010 and 11. And then 2012, it came back with a vengeance with the largest number of cases reported, 173 cases of neuroinvasive disease, encephalitis, often with brain damage and so forth, and 21 deaths. So this was a huge occurrence. So afterward, we looked it up, started investigating, and wrote this paper in JAMA, which really we were unfortunate to have the epidemic, but fortunate to have more data than anyone else had ever had. And so we were able to answer a bunch of questions. One of the questions is, did weather have anything to do with it? And what we found is that year, or over the 10-year period, the biggest predictor, the strongest predictor of whether you would have a big epidemic year was the number of hard freeze days in the winter preceding that spring. And here is 2012, the epidemic year, with 0 hard freeze days. 2006, the other epidemic year, was here, and here with more freeze days were all the years in between, and 10 and 11, where we had no cases, we had the most hard freeze days. Same thing with the departure of temperature from normal. The year with the greatest departure from normal, the most hot days and so forth in the winter, was 2006 and 2012, the epidemic years. So that got me interested in climate change, since climate change is creating more warm winters, fewer freeze days, and more departures from normal weather. So I decided that I better study climate change, because it's controlling what I do, which is mainly infectious disease epidemiology. All right, so the question was our epidemic caused by, or at least amplified by, climate change? And so, of course, there was a lot of evidence of climate change happening. So for you, I want you to just take an inventory of your own thoughts at this point. Do you believe in climate change? Now, you probably have a pretty strong view, because I remember when I was doing this back in 2003 and 4, when I began, I went around asking my colleagues on the faculty. It was a bunch of very evidence-based scientists, medical scientists, and everybody had a strong view, most that it was a problem, but some that was not. And I asked them why. Why did they believe that? What was the evidence? And they had no idea. None of them had the slightest idea what the evidence was. And I thought, that is really weird for a group like that to believe something strongly and not know the evidence. So I decided to commit myself to really studying this. And here we go. Here's your reading list. I'm sure most of you probably know a lot about it, but if you're new to it, I suggest, or not, I suggest the NASA website, climate.nasa.gov. Great introduction. There's lots to see there, a lot of updated current information. Michael Mann's book, Dire Predictions, Understanding Climate Change, the Visual Guide. This is a picture book of climate change, very sophisticated though, and a very good read. Second edition's out. And then if not, and then if you want to go further, there's a lot of other things, but the Intergovernmental Panel on Climate Change has the last 3 reports, the 5th, 4th, 5th, and 6th, are all worth reading, although it's very difficult reading. But if you're really serious, you can plow through it, and after a while, you get the lingo, and you can understand it pretty well. Okay, so in all this reading, it finally occurred to me that at first I was very, very confused about all of the evidence, and then I had a breakthrough, and that was realizing that the whole issue of climate change is not one question. There are really 4 separate questions that you need to address. And it's by breaking it up into these 4 different questions that you really get a handle on what's happening and where we should go. And the 4 questions are, is the Earth's surface temperature warming? Okay, a nice empirical question, could be answered. Is the warming due to human effects or natural phenomena? Is the sun getting hotter or whatever? Or is it human effects, carbon burning? Third one, is the warming climate a serious threat to humans? And fourth, should society invest in curtailing climate warming? All right. Notice the first 2 are straightforward empirical questions, evidence. That's all we need. Whereas 3 and 4 are partly evidence, but partly judgment, a judgment issue. Notice, is it a serious threat? Well, that calls for a value judgment. What's serious? And should we invest? Well, investment is an opinion, and whenever you invest and want to change things, you set up a situation where you have winners and losers. And if you're one of the losers, then you may not want to do that, and you may want to work hard against it, and so forth. So anyway, knowing that there are 4 separate questions, I think, is very helpful. Okay, so let's take them one by one. So is the Earth's surface temperature warming? All right, this has been studied thoroughly, and here we have graphed the 10 of the main published studies that have reconstructed temperature, Earth's temperature back to 1,000 years ago. This is from ice cores drilling down, so you can go well down to 1,000 years or more. Tree rings, coral, drilling into corals, sediments, historical data, decadally smoothed information, moving averages over the year. Here, the redder lines are more recent studies, and the bluer and the black black lines are longer ago studies. And you notice they all show that there was a slow cooling going on over 1,000 years, and then suddenly, in the late 1800s, around 1900, there was a suddenly dramatic shift and an up climbing of temperature. And this has been over and over studied. Also, here's one where you go back 2,000 years and you see the same thing, a slow downward drift, and then suddenly a giant upward swing. This is since the Industrial Revolution, and you see here the tail end of the downward slide, and then a steady uptick, but at a modest slope. And then suddenly in 1980, you see a dramatic change in slope. And since then, we've had this basically runaway warming that we've seen. But it's important to know that it was fairly slow up until the 1980s, and then something new kicked in. Okay, now if the Earth's surface is warming, there are many other things that you would predict would be happening secondary to that, and here they are, at least some of them. Well, here's the land surface air temperature, and it's going up, of course, and here's the 1980 period up to there. Sea level rise, there's a steady rise in sea level, very small, but there it is. Specific humidity, you know, as the air gets warmer, it holds more water, and so the world is getting more humid. Those of you who grew up in Texas may remember back when we were children, it wasn't as humid as this, and now it's more humid, and that's real. The amount of heat in the ocean is going up, absorbed into the ocean. As a result, the amount of snow cover is declining. The glacier mass is decreasing, and the amount of sea ice is going down. So there's a consistent picture that what's happening in warming is now translating into all kinds of secondary effects. These are the most readily measurable. Now, melting has a particularly important implication for the ice sheets of the world. And whether you knew it or not, I didn't know it before this, there are 3 ice sheets, major ice sheets in the world. The North Pole or Arctic ice sheet, and you can see this gets bigger and smaller, bigger in the summertime and smaller in the winter. And here's September, several years apart. And you can see here is the slope of the relentless decline of this surface area. Here's Greenland right next door up there in the northern climes. And here's the big ice sheet on Greenland, and getting smaller. But then the big kahuna is the South Pole, Antarctica. And there's the west ice sheet here, and then the eastern ice sheet. And this contains 3/4 of the world's fresh water is contained in this land mass. Okay, now notice that these are land masses, Greenland and Antarctica. The Arctic is not a land mass. Remember, this is floating ice. And if you remember your iced tea from lunch today, if you had lunch, if your iced tea, if the ice in your iced tea melts, okay, the iced tea does not overflow because melting ice does not increase the level, okay, when it melts. But if you were to pour water into your iced tea, obviously it would run over. So you see, ice on land, when that melts, that increases sea level. But when Arctic melts, it doesn't increase sea level. But I'll show you later that this has an even more dire implication for the world than even the melting of the big kahuna here. Now, another very important basic fact is that the rate of warming is not the same all over. There's big differentials. Notice that the land masses are warming more than the sea masses, okay? So land warms more than sea. the northern hemisphere warms more than the southern hemisphere, and the Arctic is the worst. This is warming 3 to 4 times more than the average of the world. Okay, so if the world has increased by 1 degree Celsius, which is a fact, this has increased by 3 or more degrees by now, and now we're starting to see 80-degree days in the summer in the Arctic, which were never seen before. Okay, so this will be important to talk about as well. And just to show you how consistent this is the seasonal temperature of the world, and you can see back in the early in the industrial age, from there on up, it's just a progressive increase, and the entire curve is being displaced upward. Okay, so is question 1, is the Earth's surface temperature increasing? Undoubtedly, yes. Who would doubt that? Okay, question 2, is the warming due to human influences or natural phenomena? All right, here's the model of the greenhouse effect. I'm sure you're familiar with this. The sun is the main source of energy for the world, okay, and it shines light energy that's then absorbed on the Earth's surface. Some of it is reflected back into space. Clouds reflect more of it than ground. Ice reflects more than open ground or open ocean. Okay, they absorb more, ground and ocean, because they're darker, right? But then what's interesting is at night, after the sun has warmed the surface area here, at night you get radiation, infrared radiation, projecting a lot of that heat back out into space. Okay, it's like sitting in front of a fireplace. The fire is not burning you and keeping you warm. It's the radiated heat coming out of there. Well, that's what goes up into the upper atmosphere and out into space, thus cooling the Earth. However, there's this layer in between the upper troposphere where we live. We live in the lower part, but in actually pretty much throughout the troposphere, these greenhouse gases can accumulate: carbon dioxide, methane, nitrous oxide, ozone, chlorofluorocarbons, and water. Actually, water vapor is a greenhouse gas as well. Clouds are a greenhouse gas. Okay, these accumulate, and what they do is they trap the infrared radiation and reflect it back down to the surface at night. So they prevent the loss, and then they warm it. If you've ever been on a camping trip and you were sleeping there and it was nice and warm while you were sleeping, and suddenly about 2 o'clock in the morning you got real cold and you looked up and there were the stars. It had been cloudy early and the clouds moved away, and now it gets real cold all of a sudden because all that heat's suddenly dissipated. It's a very powerful radiation, loss of heat, and when you don't have that, then the world warms. Okay, the greenhouse effect is not new. It was described by Joseph Fourier in 1824. John Tyndall measured radiative properties of many gases in the 1850s, but it's really attributed to Svante Arrhenius, who quantified the greenhouse effect. He published this in 1896, saying that the greenhouse effect is a simple matter of physics, what he called the greenhouse law, that the change in the atmospheric temperature, it will increase with the logarithm of the carbon dioxide concentration of the atmosphere. Okay, and he predicted that industrial carbon dioxide emissions were sufficient to cause global warming a little bit, but he said, and he said if you doubled the CO2 level, that you would increase the world's temperature by 5 degrees Celsius or 9 degrees Fahrenheit. And he got the Nobel Prize, first Swede to get it for this and some other things he did. But his main prediction was, don't worry, our industrial output could never produce enough CO2 to do this. Okay, there was his one error. All right, so how are we doing? Well, this is the carbon dioxide concentration of the atmosphere in parts per million. Okay, and It started back around 290 before the Industrial Revolution, 280 to 290 for many millions of years back. And suddenly it started increasing. This is measured by ice cores and so forth. And then starting in the late 50s, they started measuring it on the Mauna Loa volcano, the top of this at that time extinct volcano. And when it's not erupting, they measure this. And this is, I'll show you in a minute why, but so you see this relentless rise and in CO2 concentration, and you see down here now the liberation of carbon emissions by their sources, and you see here coal, oil, and gas and cement making are the main ones. The main culprits releasing all this carbon to the atmosphere. And you see these two curves are approximately collinear here, okay? And now it fluctuates in winter and summer, okay, but it's a relentless rise. Here's the output of carbon into the atmosphere. And over time, since the Industrial Revolution, we have let loose over 1,000 gigatons of carbon dioxide. Now, you know what a gigaton is. A gigaton is 1 billion tons. So we've liberated 1 trillion tons of carbon dioxide into the world's atmosphere. 46% of that remains in the atmosphere, in the air, and 30% of it has dissolved into the ocean, thus acidifying the ocean, which is we should really have a whole nother talk on the effects of ocean acidification, because it's probably about as serious as the atmosphere, which we're going to mainly focus on here. Here's the Mauna Loa volcano on the Big Island, okay, of Hawaii. Here's the reason this is good is that this is the prevailing winds are blowing vast air from the Pacific Ocean over this, and so it's thoroughly mixed, and the closest you can get to the air that is not influenced by human activity in the immediate vicinity. So that's why they do it there. Also, to keep it in perspective, CO2 is a very tiny amount of gas in the atmosphere. 78% is nitrogen, 20%, 21% is oxygen. Only 0.041 is carbon dioxide, or 41 per million, 410 parts per million. But that is enough to be very, very active in terms of greenhouse gas effect. Okay, now here's some more numbers down here, and these I want you to really remember. Pre-industrial, the largest it had ever been was 300 parts per million, ever, in at least 650,000 years, and really over 34 million. And it was mostly 280. There were a few spikes a little higher than that, but not much. And the upper limit for the past 35 million years is 500 parts per million, okay? Today, I just looked it up this morning, today we're at 414 million parts per million. 414, whereas 300 was the most it's ever been in 650 years, okay, and 500 in 35 million years. Now, a brief word on methane. Methane is a natural gas. It's natural gas that we burn. Human emissions are from natural gas production and leakage from gas wells and pipelines liberated into the air, and from our homes to some extent. Natural emissions of methane come from anaerobic decompensation of plant matter, just from rice production in general. Rice production is a major source of methane, and livestock belching and volcanoes. Okay, methane is interesting because it remains in the atmosphere. If you release some today, those same molecules will be here for about 10 to 20 years, and then they'll disintegrate and their effect will be lost. Carbon dioxide remains in the atmosphere for centuries. So this is a long-term threat, but this is a short-term threat. Okay, so global warming potential over 20 years. So what they call the GWP 20, global warming potential over 20 years, is 86 times greater than that of carbon dioxide. But you'll also hear this 28 to 36 times. That's the global warming potential of a molecule released today, averaged over 100 years. Well, it only lasts for 20 years, so this is kind of a bad statistic. You see, it's really what we're releasing now will be 86 times greater than carbon dioxide for the next 20 years. And that's what counts right now. Now, this is, I think, one of the two most important slides of the whole thing. This is the thing, I heard a talk by a climate scientist up in Crested Butte at the Rocky Mountain Biological Lab several years ago, and this really got me intrigued, and I've been studying this ever since. And this is the atmospheric CO2 level for the last 650 years. Okay, here's where we are approximately today at 414 parts per million. Notice the CO2 level has fluctuated over time. Look at this. About every 100,000 years or so, you get a dramatic increase in the carbon concentration of the atmosphere. It goes up to about 280 or so, and then it kind of levels off with maybe a slow decay, and then suddenly it starts falling and it goes down. Well, when it goes down, that produces an ice age. It's called the glacial period, and these temperate periods are called interglacial periods. So the interglacial periods and glacial periods. And these keep repeating. And you can look back 34 million years, and it's been this way for 34 million years. And what produces this, there are theories, I don't think anybody think this is proven, but somehow there are massive quantities of carbon suddenly released into the air. Now, suddenly means in 1,000 years. This is about 1,000 years here, okay? So it's not, but notice that huge upswing and then the slow decay, all right? Notice what we've done. Here was the last massive increase like this, and then decay, and then this was the beginning of the Industrial Revolution right here. Look at this, okay? And what have we done? Okay, in the last 100 years, we have gone way beyond where we've been in 34 million years, and we've done it in 100 years, not in 1,000 years. So we are just, we are telling the Earth, hey, take this. Let's see what you can do with this. I don't believe you can do anything. I mean, what are we doing? All right. Now, this is related to the wobble of the Earth's orbit. The Earth's axis. You know, it wobbles like a top slowing down, and it does this about every 10,000 years, I think. But of course, that's happening over and over. For some reason, it's thought that somehow something sets off this, and then it's aided and abetted by this phenomenon. I'm not sure I quite understand all the theories, but anyway. So the question is, why does that happen, and what's going to happen now? Okay. So now, is the buildup of CO2 coming from natural causes or anthropogenic, human causes? Okay. For example, has the sun gotten hotter, or and warmed the Earth as a result? Well, we can answer that one quickly. We've been measuring this since 1880. Okay, and it turns out the sun, the amount of heat from the sun does fluctuate. See, all right, but there is a trend here that shows that it was increasing from 1880 up to, what is that, about 1950. But since then, it's been going down. It's been getting cooler, and this is typical of over a long period of time. But here is the temperature of the Earth's atmosphere, this same hockey stick curve I showed you a while ago, and you see while this has been dramatically going up, the sun has been getting cooler. So this clearly is not the explanation. Okay, here's a second fact. Here is computer modeling, supercomputer models that are getting very good these days. The blue is the predicted level of temperature of the troposphere, that is down near the Earth where we live. This is predicted if no man-made effects were at work. So if there were releases of methane, natural releases of methane, sun fluctuation, volcanoes, etc., it would be on the blue line. And here, of course, is what we actually measured. You see here an instantaneous drop due to a volcano. It actually slows down. It actually reduces the temperature because it produces soot into the air that then blocks a lot of the sun's rays for a while. Okay, so it's getting warmer down here by direct measurement. Well, it turns out we can now measure this in the upper atmosphere, in the stratosphere, and it turns out here's the prediction for it to remain the same. Here's what's actually happened. While the troposphere is warming, the stratosphere has been cooling. Now think of that. Why would that be? Well, if the sun was getting hotter, this would be warming because it's closer to the sun. What this, though, suggests that it's the greenhouse effect, that these greenhouse gases are blocking the escape of heat into the upper atmosphere, and that is cooling the upper atmosphere while it's warming the lower atmosphere. Fascinating, isn't it? Here's more evidence. Turns out when that infrared energy is radiated back out into space, and some of it is reflected back to Earth, you can actually look at the spectrum of that ultraviolet infrared radiation, and there are certain components of that, parts of the spectra, that are radiated back more than others. And it turns out these parts of the spectra that are more prolifically radiated back happen to be the parts of the spectrum that are radiated back by the greenhouse gases, carbon dioxide, ozone, methane, and so forth. See, so it's not all of the infrared radiation is coming back. It's just those parts of the infrared radiation that are sent back by these greenhouse gases. That's in the lower part of the atmosphere, what's reflected back. And then here's an experiment that was done to see what is going out into space. Over a 26-year period, they measured what infrared energy was coming out into space. Okay, and here is the change over these 26 years from 1970 to 1976, the change in radiation, infrared radiation escaping into the upper atmosphere. And you see the parts that have decreased are the parts that are blocked by the the greenhouse gases, CO2, chlorofluorocarbons, ozone, chlorofluorocarbons, and methane, so forth. So you see here, the radiation that's coming back is that brought back by the greenhouse gases, and that which is not, failing to get out into the space is the part that's blocked by the greenhouse gases. So here is very strong evidence that it's the greenhouse effect. Now, is it the greenhouse effect? Where is the carbon coming from that's producing the greenhouse, the CO2 in the atmosphere? Well, you remember from your high school chemistry that oxidation of carbon is burning. So burning occurs when carbon is combined with one atom of carbon combines with 2 atoms of oxygen. That then releases heat, which is the heat of burning, and that produces 1 molecule of CO2. Okay, so every time you produce 1 molecule of CO2, you lose 2 oxygen atoms from the atmosphere. Well, it turns out they've actually measured this in several different studies on the Mauna Loa volcano and at the South Pole. You get agreement on the measurements. And here is the rate of appearance of carbon dioxide molecules, the increase in CO2 in the atmosphere. This is the rate of loss of oxygen from the atmosphere. Now, this isn't enough to starve us of oxygen. This is a tiny, these are tiny changes. But notice the slope of this is exactly twice, and the inverse, twice the slope of this. So oxygen is departing at twice the rate that CO2 is appearing, which is exactly what you predict if this is coming from the burning of carbon. Now here's even a better, this is the atomic proof, okay? Carbon has several isotopes. Two of the most important for us here are carbon-12, which has 6 protons and 6 neutrons, accounting for atomic weight of 12, and carbon-13, which has 6 protons and 7 neutrons, okay? Well, in millions of years ago, photosynthesis was a more primitive process, which has evolved since then. But back then, photosynthesis primarily produced or took up carbon-12 and produced it into plants and biological matter, okay? So it incorporated carbon-12 where it sits. Whereas in more recent millions of years, certainly now, carbon-13, the newer photosynthesis incorporates carbon-13 more. So more recently produced carbon that's for plants or belching cows or whatever, that carbon is full of carbon-13. It's got a little carbon-12, but more carbon-13. So what you would predict is if the climate change or the change in increase in CO2 in the atmosphere, if that is from burning of fossil fuels, that is dinosaurs and plants that were laid down and turned into oil millions of years ago, you would have more carbon-12 coming into the atmosphere. Whereas if it was recently related, stuff from cows and rice and that sort of thing, it would be more carbon-13. Well, here for the last 1,000 years, here is the level of CO2 in the atmosphere. As you can see, that's our familiar curve, all right? Whereas here is the ratio of carbon-13 to carbon-12. And so you see it coming along here, and all of a sudden, in a mirror image to this, you see it dropping. That means the amount of CO2, the carbon, as CO2 is being added, the amount of the ratio of carbon-13 to 12 is going down. So that means we're adding ancient carbon to the atmosphere. Whereas if it was cows and rice and so forth, this would be going up at the same rate as this. So molecular proof that it's burning of ancient carbon that is is where all this carbon is coming from, the burning of prehistoric carbon. So to answer our question, here's the evidence implicating fossil fuel burning. Theoretical explanation of the greenhouse effect by Arrhenius. The atmospheric CO2 level track CO2 emissions. Oscillating CO2 levels for 4.5 million years, actually for 34 million years, has now exceeded. So this is an unnatural event. Solar irradiance is not increasing, it's decreasing. Tropospheric warming is with stratospheric cooling. Reflected infrared energy in spectra of the greenhouse gases. Oxygen disappearing at twice the rate of CO2 appearing. And the atomic proof decline in the carbon-13 and carbon-12 ratio. So the answer to my second question, the scientific evidence clearly shows that the warming is largely due to human emissions of greenhouse gases, primarily CO2 from burning fossil fuels. Okay, third question. Is the warming climate a serious threat to humans? All right. Here is our familiar curve up to about now. We're about here now. This was drawn several years ago. And there are several scenarios of what's going to happen to the CO2 level and how many degrees of warming there's going to be over before 2100. It turns out if we really stop burning fossil fuels, alternative energy and all of that, this could actually go down, particularly if we suck some of it out of the atmosphere. This might go down. Whereas if we have only modest decrease, which right now looks like it might be possible, but it's not happening, it would be here. Whereas if we continue the way we're going, it's going to be here, and we could even start burning more if certain elements take over the world. We'd burn more and we'd be there. This is 3 degrees Celsius. This is 2 degrees Celsius. It's where we would be if we take action. And 1.5 is where now the latest reports of the IPCC say we better keep it below 1.5 because 2 degrees would be catastrophic. And what would it do? It would threaten our food supplies, water supplies, human health, coastal cities, energy production, national security, economic prosperity. Okay. And if the current rate of fossil fuel burning continues, we will reach the point of irreversibility somewhere between 2030 and 2046. So somewhere in here, it will become irreversible, and whatever path we're on will continue no matter what we do at that point. And I'll show you why in a little bit. Okay, now I'm not going to spend a lot of time on the ill effects. You all probably know that, and you can read that. There's tons of literature on it. Let me mention extreme heat waves. We're seeing it. Changes in precipitation, dramatic. Longer frost-free seasons, some part good, but it's increasing vectors and earlier epidemic conditions. Increasing tree diseases, die-offs, deforestations, just naturally by the temperature. Ocean acidification, huge problem. Fish species are already migrating north to get away from the heat. Species that can't adapt will decline, and we're seeing some of that. Species extinctions by threatened food supplies. Disappearing glaciers threaten water supplies. A lot of our western cities particularly, their summer water supply is from the melt of glaciers. If the glaciers disappear, they're up the creek. Oh, sorry, bad analogy. More rainfall in the Midwest, okay? More droughts in the Southeast and Southwest. Stronger storms, higher grade tornadoes and hurricanes, more hailstorms, sea level rise, eventual loss of coastal cities, etc. Medical, from a health point of view, I'm sure you've read articles on this. Increased vector numbers and efficiency. West Nile is an example. Expanded range of vectors. I'll show an example in a minute. More rapid emergence of novel infectious diseases. Increased asthma and COPD, exacerbations, heart attacks from air pollution. Air pollution gets worse under climate change scenarios. Increased allergies and asthma from higher pollen production, longer algae seasons, greater risk of foodborne and waterborne diseases, more extreme heat waves, etc. Increased severity of extreme weather events, people killed by hail, tornadoes, hurricanes. In the future, perhaps whole cities wiped out by superstorms, famines, drought, etc. Okay. So here's remind you of the effect of climate, we think, on producing this West Nile epidemic. Here's an interesting one. Here is the traditional range of overwintering of the Aedes aegypti mosquito, which brings you dengue, yellow fever, Zika virus, etc. And when Zika broke out, CDC got real interested, and they hadn't mapped this in, I guess, 40 years. We went back and remapped it in the Gulf. Here is now the overwintering zone. We're seeing it up in New Jersey and Washington, D.C. We're seeing Aedes aegypti surviving the winter, and up into Missouri and Kansas, and out into California and Arizona. And so in fact, we're seeing this all over the world. Here is the original range, and it's hard to see it, but it's enlarging, okay, all over the world. Oh, and why is that? Turns out, where there are two jet streams. There's the northern jet stream and the southern jet stream. And these demark the equatorial zone, and the tropical zone is between those. And it turns out as the Earth warms, these jet streams migrate poleward, okay? So enlarging the tropical zone. And we're already seeing that happen. The tropical zone used to end in South Texas, and now Texas is putting its tiptoe into the tropical zone, and that will continue as climate change gets worse. Threats to national security. This is one people don't think about, but it's important to make this. This is what the Pentagon's been worried about for decades now, and are planning for this. The Arab Spring 2011-2014 was immediately preceded by a once-in-a-century winter crop failure in China that inflated global wheat prices. The top 9 wheat importing countries are in the Middle East. You may remember the headlines. They had huge price increases throughout the Middle East, leading to revolutions over other pit-up stresses. Okay, and they were poorly managed, so that, of course, then they were taken over by dictators and so forth, and fizzled back into despotism in many places. The Syrian civil war is particularly interesting. This really came out of the blue. Syria was thought to be immune to civil war. It was preceded by 4 years of the worst drought and crop failure in its history. Crop losses were 75% or more. Sheep herders lost 85% of their sheep. Hundreds of thousands of wells were drilled, draining the aquifers. People then massively migrated from rural areas into the cities, crowding, lack of shelter, food, infrastructure, poor government handling ignited Syria, and of course, we're still paying for that. Countries are already competing for control of the commercial passages and mineral rights opened up by the melting Arctic. The Northwest Passage is now there for the taking, and we're starting to, the Russians are planting flags on the ocean bottom up there because they're going to try to take it, okay? Accelerating crop failures are stimulating northern migration in Central America, are stimulating northward migration. Just a brief word on that. The severest droughts in the Western Hemisphere are in Guatemala, El Salvador, and Honduras. Guatemala, El Salvador, and Honduras. This is where the worst part is. And that hit the peak in 2018, which you may remember was the election year. Remember all the caravans? Well, 28% of all asylum applications at our border, southern border, were from Guatemala, El Salvador, and Honduras. Only 7% were from Mexico. So here's where the people were coming from. UN studies down in Central America show that 1.6 million people in Central America face food insecurity from climate change. Okay, and they studied these caravans and found that this is a World Food Program survey. Half of the Central American immigrants left Central America because of the lack of food. And here's how it works. Climate change causes temperature fluctuations, shifting rain patterns, droughts, crop failure. There's now an epidemic of coffee rust, blighting their coffee crops, and big hurricanes. These wipe out the farmers, and many of them come right to the United States, immigration north. Others, actually larger numbers, migrate to their cities, just like in Syria. This leads to infrastructure being overwhelmed, crime and exploitation. Then they come north. And this is what, you remember people were saying, well, they're coming north because of crime and exploitation. Yeah, but why is that? Why has that gotten worse all of a sudden? Well, it's climate change. Now, what's the implication of melting ice sheets? Well, if Arctic melts, remember there's no increase in the sea level. But if Greenland melts, there's 20 feet of ice in here. In other words, if this melts completely, oceans will go up 20 feet. Not 2 feet, 20 feet. If the western ice sheet of Antarctica goes into the ocean and melts, 10 feet of rise. But if the eastern ice sheet of Antarctica goes 190 feet of sea level rise. Now, is that possible? Well, there are efforts to answer that question. Remember my graph here? Well, there is something that is a force here that has not been incorporated into the models. So this has not been incorporated into the models that projected this, okay? Because there's a phenomenon called feedback loops. And the dire effects of feedback are a huge threat that are not well appreciated, certainly by the public, and are now only now starting to be incorporated into the modeling because the supercomputers weren't big enough. What you got here is what explains these huge fluctuations. Well, somehow a huge mass of carbon was released all of a sudden, okay? Where was the carbon coming from and why was it released? Okay, it had, and the answer is it has to be some kind of massive positive feedback loop between temperature and biological ecosystems, because that's where carbon comes from, is biological systems and their leftovers. So there must be massive amounts of carbon sequestered where it can be released by warming. And it turns out there are several sources. The biggest one are massive fields of what are called hydrates. These are frozen sheets of carbon dioxide and methane down at the bottom of the ocean, mainly around Antarctica. And it's thought that a lot of this is when Antarctica melts, and then suddenly these hydrates start melting and bubbling up this, and you get a massive outpouring in a short period of time. All right. And also the methane from the tundra in the northern hemisphere. Okay. Remember, the warming is not uniform. You know, the northern hemisphere is worse. Ice and snow-covered surfaces up here normally reflect sunlight back into space and counteract warming, but land masses exposed by this excessive heat here absorb more light and heat faster. So melting ice exposes land and ocean, more light is absorbed, more melting of ice occurs. Positive feedback. Vegetation absorbs carbon dioxide and takes it out of the air, sequesters it in the ground, right? We all want to plant trees and everything to solve greenhouse gas. The problem is when the earth heats, you get droughts and then forest fires and development come in there, cause deforestation. When these forests are killed, their roots decompose and release all the carbon that was sequestered down there, mostly as methane, with 86 times the heat trapping of CO2. So you see, vegetation sequestering is only a temporary thing, although there's some new techniques that would make it permanent, but we're not really using them, okay? Here is the Arctic tundra. It's composed of plant and animal matter deposited and frozen over millions of years. It's up to a mile thick. Here's a cross-section photograph, up to a mile thick. Warming, remember, is 3 times higher in the Arctic, so it's starting to melt this. This is what's called a permafrost crater. This is where it starts, and then it eats away and eats away. It's like a decubitus ulcer. It's a medical audience, so I can say that. Eats into it and melts it all the way down to the bedrock. Okay. This is thawed. The thawed organic matter then putrefies, releasing methane and some CO2, mostly methane. And there is enough methane and carbon dioxide in the Arctic tundra, which, by the way, extends all the way around the northern part of the globe, you know, Siberia and all around. There's enough carbon here to release the equivalent of 1,600 gigatons of CO2. Do you remember how much have we released already? How many gigatons of CO2 have humans released? We've released 1,000, and only, what, 46% of that, so 460 are in the atmosphere. And look what it's done. What if 1,600 gigatons gets released into the atmosphere. You see, this is a catastrophe. And so continued progressing of melting eventually releases monthly greenhouse gases equivalent to China's output right now. So this would be soon, very quickly, a tipping point that would make this, the game would be lost. Okay. Here is actually a picture of an Arctic lake, a newly formed Arctic lake in Siberia, formed by melting of the tundra here. And these are bubbles of methane bubbling up from the putrefying tundra down in the bottom of the lake. All right, now here's the scariest finding. This is James Hansen's recent article, 2016. Very fabulous article. He's got a dream team of scientists from many different fields collaborating on this long-term project. They studied what happened here. They went back to all the geological record, the fossil record, all sorts of things, climate research and so forth, and put together a picture of what happened here to see what would happen if this occurs now, if this thing is let loose now. Okay, when global temperatures reached only slightly higher than today, large chunks of polar ice disintegrated with a quick rise. So first thing that happens, Antarctica started melting, and you got 20 to 30 feet real quickly. That's in the geological record. It's generally agreed this is going to happen, but most people think it's going to be over centuries, 20 to 30 feet. We're thinking 2 or 3 feet maybe by the end of the century. The new finding is that this will happen abruptly over the next 50 years, destroying most of the world's large coastal cities. Why? This is a phenomenon called the ocean conveyor belt, or the thermohaline circulation in the Atlantic Ocean. Basically, here's what's normally happening. Warm surface air is flowing in big currents north toward the North Pole, cooling as it goes. By the time it gets here, it gets very cold up in the North Pole and quickly dives down to the bottom, where it then circulates back down to Antarctica and then circles around Antarctica, keeping it cold. So this is the ice box that keeps Antarctica cold. The problem is, 120,000 years ago, the Arctic ice sheet in Greenland melted, throwing a huge amount of fresh water into this Arctic Ocean up here, changing the salinity of it. And this current is propelled by temperature and salinity, the salinity gradient. So if you eliminate the salinity gradient, suddenly you stop the circulation. It slows down and then it stops. What that then does is result in cooling of the northern hemisphere and warming of the southern atmosphere, which then melts the South Pole faster and produces another ice age up in the north. This was thought to be the reason for the ice age when this happened. And they also forecast from this that due to the changes in the temperature gradients in the Atlantic Ocean, you get superstorms generated that are many times more violent than anything we've ever seen in human history, okay, or really human prehistory. They're just hugely violent, with huge violent winds, major changes in temperature, colossal rains, etc. And here is one of their pieces of evidence. This is from that period of time. They see these mega boulders in several places. This is a boulder that was thrown up on a 20-meter high, 65-foot cliff by these huge monstrous waves. Here's a person standing here as a reference. Okay, so violent enough to throw boulders this size up on a high cliff. So that's what we're in for. Now, how bad could it get? Well, this is the the fossil geological record for the last 600 million years. So 600 million years is over on the right, and today is on the left. Sorry, it's kind of backwards, but that's the way this is drawn. This is the CO2 level on the vertical. Notice back in geological history, CO2 levels have been as high as thousands, 4,000. Remember, we're at 400 right now, 414 down here. They were in the 4,000s range. Well, the fossil record shows there have been 5 major extinctions, shown by the arrows here. These are the 5 major extinctions. Here's the last one when the KT event occurred. You know, the asteroid hit the Yucatan Peninsula, kicked up, produced a massive change in the weather and extinguished the dinosaurs. Okay, but here are there are 5 of them. All of these occurred with at the point of abrupt increases in CO2 levels. Okay, and turns out it has stabilized now primarily due to change in the tectonic plates. It's thought that CO2 levels have trended downward the last 100 million years. But it was not, well, here is the period of 34 million years where we've had this cycling of the CO2 levels, the glacial, interglacial periods. This phenomenon was there. It's that long. Here's the, I'm sorry, here's the glacial, interglacial period, 34 million years. This is the how long the eastern Antarctic ice sheet's been there and the western ice sheet. Here is the period of hominid evolution, resulting in the evolution of man about here. This green arrow is the time when large mammals began evolving. So you could not get the survival of large mammals until the CO2 level got below 500. Okay, we are now at 414, and 500 was the limit at which large mammals could evolve. Because remember, when CO2 goes up, we breathe CO2 in and out. And remember what happens when you're hypercarbic. Okay, so now, is this serious? Should we worry about this? Okay, remember this, here are the bad things that can happen. Here are the scenarios. Which one of those are going to be happening? At one point, as I was thinking this up several years ago, it suddenly hit me. This is my lifespan. If I'm lucky, I might live this long. Here's my children's lifespan. And here's my grandchildren's lifespan. My grandchildren, whom I see not as much this month as I have in the past, but every time I see them, you know, I worry, what is their life going to be like? You know, if this thing happens. My conclusion, third question, and really the fourth question, yes, global warming with climate change from human emissions of CO2 and other greenhouse gases is no longer a debate within the scientific world, no longer a debate. It's not an issue of faith that you believe in or not. It's science. It's rapidly growing threat to our children's future. It can be constrained by action in the next 11 years, and time is passing. So should we invest? Okay, here's my short list of what we need to do to keep it below 1.5. We need to scale up non-polluting power, solar, wind, geothermal, tidal, and this new traveling wave technology. Have you heard about that? If not, go on Netflix and look at the video inside Bill's brain. This is a fabulous thing of something that he funded. It's ready to be demonstrated, and China was going to do it until the Trump administration blocked it. Heliopower and heliofuels. Look up Heliogen, the company Heliogen, a huge breakthrough that will make solar and power easy and non-polluting. High-tech job creation will be far outstrip what fossil fuels will do. Transition government subsidies from coal extraction and fracking to major support for energy renewables, emerging renewables. Transition electricity generation to safer, traveling wave technology, manufacturing to heliopower. Here's how the sun can drive manufacturing with very high temperatures. Transportation of all electric and all hydrogen helio fuels. You can develop hydrogen fuels with no pollution, no energy use with these. Since CO2 remains in the atmosphere, causing global warming for centuries, we've got to remove it from the air and sequester it deep in the earth to manufacture products. Strong federal government leadership is important, and investment to scale up quickly. And U.S. government must exert leadership on China and India, developing countries to follow our lead. I know I'm over my time, and I'm really sorry, so I'm just going to deal it up with this. Skepticism is withholding belief because evidence does not live up to the standards of science. This is good. It's what we live by. Denialism is refusing to believe something in the face of what others believe is compelling. Here are all the organizations that buy into climate change, that we need to do something. And here's the reasons that people don't do it. But let me get you my final quote. Here was Father Theodore Hesburgh, president of Notre Dame, in his 1988 speech on the nuclear dilemma, the greatest moral problem of all time, nuclear disaster. What do we do about this monster that we have created, nourished and developed to a point where its nefarious power today is literally 1,000,000 times greater than in 1945? We all know that we are the first generation of humans since Genesis that can totally destroy the human species and make our beautiful planet uninhabitable. Well, we are now the next generation of such humans. Okay, remember your children and grandchildren, and that's the end. Okay, if we have time, I'll take some questions.
Thank you, Dr. Haley. For those that are participating in our webinar, we do have a question box. You'll see a question mark on the side of your screen. So you can go ahead and type your questions in there, and we'll go ahead and if we have any questions, we'll get those to Dr. Haley right now.
We did receive a question from Christine. The question says, can you talk a little bit about fracking and the carbon release it causes? People talk about fracking in the media as it is a transition fuel or better than other fossil fuels, but is not a good option? Isn't it not a good option? Sorry.
Okay, well, it depends on whether you're thinking short-term or long-term. There's no doubt that fracking, primarily to produce natural gas, and that natural gas has been an improvement. But it's got about half the CO2 release of coal. So for the long term, it's bad. For the short term, it's been good. If you discount then the local effects, there are some pollution effects that affect people's health in various communities. But we need to phase it out along with carbon, along with coal burning. So the key is we need to stop investing in fossil fuels and start investing in renewables that are non-polluting. It's interesting, I didn't really get into this, but this is happening rapidly. The change in investment is rapidly. You know, most investment in fossil fuels is not from the government. There is a lot, but it's from private equity investors. They are rapidly divesting, and you know, there's this firm BlackRock, which is the largest pooled investment fund in the world. It's the big kahuna. The head of BlackRock basically makes policy for the investment community in all fields of investing. And what, 6 months or 8 months ago, they announced they were divesting. All their funds were divesting, and they're advising all of their clients to divest of fossil fuels. Many universities have already divested. And so this is going to dramatically reduce the amount of funding that fossil fuels have to drill and to produce fossil fuels. So it will die out. The problem is, will it die out fast enough? And so we need a race for the non-polluting fuels to run it off the playing field.
So We have another question from Charlie, looking for your thoughts on the policy, the Green New Deal. Do you think that this is going to be enough?
That's a very good question. And it's partly a political question. Certainly there are many, many good things about it. The fact that it's so polarizing has not been good, although that may be less of a problem in the future. We'll see in the next election and so forth. But I really think we need, I don't want to be wedded to any political plan, because there's so many things that go into doing those other than the science. And so I think we need to keep our eye on the ball, which is, what are the best technologies for non-polluting fuels to replace carbon, and be sure that our decision makers are investing in those. And I'm not sure that's happening, because there's a lot of sort of faddish thinking just in all circles on this. But the other thing is, it's clear now, and there's a lot written on this now. James Hansen's written some things on it, and that is, we can't now. It's too late for the human civilization to survive just by replacing carbon and stopping. If we stop our emissions, we're still going to perish, okay, eventually. And the reason is those positive feedback systems are now being kicked in. There is methane bubbling up from the tundra and so forth. So it's clear that we're going to have to suck carbon dioxide out of the atmosphere. That is clear. And I don't hear that in the Green New Deal or in anything else. And that is absolutely essential when you read the science. It isn't going to happen without that. There are several technologies. There's one that's actually working in producing products out of the CO2 that it brings out of the carbon it brings out of the air. And they've recently opened 3 plants now in Europe, and I believe in Sweden also. And so the technology is there, but there's more technology to be invented. We need to be investing, the governments need to be investing big time in these sequestration or direct air capture technologies, DAC. That's not the quarterback of the Cowboys. That's direct air capture. Another one?
Okay. You know what? We don't seem to have any more
Oh my goodness.
questions. So I think that we're at a close. Thank you so much for your time, Dr. Haley. Doctors for Change and Physicians for Social Responsibility would like to thank all of our participants for joining us today. This webinar has been recorded, so others can please share it. The recording will be available probably within the next few hours. And I believe we also were doing Facebook Live. So go check your social media and see what other questions might be available, what other conversations might have been generated. We hope to engage in another series of conversations around climate change. Dr. Haley, do you have any closing points for us today?
Only that we all need to become knowledgeable about this. We need to study, and so that we can really defend the right scientific point of view and help channel the efforts of our societies into the most productive effort. That's my concern. Good luck.
And
Dr. Haley, thank you so much for such a well-researched presentation. That one of the comments from Dr. Singer at the Texas Medical Center was that it was just an outstanding presentation, and that it was so good to see it presented by a physician, rather than just someone who is an environmental scientist, but to really bring home that physicians understand this science, and that you have been able to help us understand and see what we're looking at, which is quite arresting and very educational. We appreciate it.
Well, I'm glad it was helpful.
excellent. Well, Thank you, everyone, for joining us today. We look forward to the next conversation and ongoing conversations. And again, thank you to Dr. Haley for a very insightful, albeit a little bit scary presentation.
Pleasant dreams.
Thanks again.
Thank
Okay.
you. We'll be
care.
signing off now. Have a wonderful
Bye.
day, everyone.